All right. Welcome back to another exciting session of CE 374U, Urban Stormwater. Let's get settled down so I can get started, please. All right, thank you. Great. It's great to see you back. A couple quick announcements before we get started. Homework 1 is due next Thursday. So please come see me or Becky at our office hours if you have any questions on homework. Again, homework 1 will be on open channel flow, uniform flow, the energy equation, which we're going to talk about today, as well as discharge control structures. Okay. So homework 1 due next Thursday. Please come see us at office hours if you have any questions. Okay. The other big item, please fill out the group formation poll by Friday. Again, the group formation poll, you can find that on Canvas. It'll ask you questions about whom you might want to work with. We'll use that to assign you to project groups for the rest of the semester, and also to determine the seating chart for the rest of the semester. Okay, so after the group formation poll gets turned in, this weekend we're going to assign groups. From those groups, we're going to assign seats, and those seats we will use to take attendance for the rest of the semester. So please keep that in mind. Also, if you have any special needs for where you sit in the classroom, please let me know. So if you need to sit near the front of the room to be able to see the screen, please email me about that. I don't think there's room in the poll for that. So please do that. I noticed that some of you are squinting during lectures. So if you need a seat near the front, email me. Another quick thing I wanted to note, I have posted typed lecture notes for everything we've covered so far. This can be found under Canvas files, lecture notes. It has kind of a nicer, typeset version of the notes for all of you, as well as any code that we've implemented in the class. Okay, so you can find that under Canvas files. Great. Are there any questions before we move on? Yes. I think so, because I responded to one student with a solution to it. But if actually, if you are, if you want to go for it, yeah, go ahead and send me your answer for the extra credit. Okay. Okay. Great. Are there any other questions? Any other questions? Cool. Okay. Awesome. We got a jam-packed lecture today. Let's just quickly review what we talked about last time. Last time we introduced uniform flow. We derived the expression for uniform flow from the St. Benoit equations. Can anyone tell me what characterizes uniform flow? There's a couple different answers you can give, but let's just quickly jog our memory. What characterizes uniform flow? It's a couple different answers I could accept. Can someone raise their hand? Yes. Right. So the depth and velocity do not vary with time or space. Any other idea? Any other characterizations of uniform flow? Yes.
The friction slope and the slope of the bed are the same.
Yes, that is also correct. So those are the two ways of characterizing uniform flow that I want you to think about. Or in other words, the friction force exactly balances the gravitational force. That's equivalent to your definition you just gave. Okay. So we talked about uniform flow. We showed how to derive Manning's equation, which essentially just combined our definition of uniform flow with an expression for the Chazy coefficient given by Newton's drag law. And we showed how you could use Manning's equation to solve some example problems. Okay, so that's what we did last time. Today, we are going to talk about the energy equation. We're going to show where it comes from. We're going to introduce and refresh you on a few concepts you may have learned in hydraulics, namely specific energy, supercritical, subcritical, and critical flow. We're going to talk about the Froude number, and we're going to go through a couple example problems. Okay, so this is a refresher. It's going to be important later on in the course. We're going to be using the energy equation pretty extensively for most of our hydraulic design. So it's an important concept for you to be familiar with. Are there any other questions before we move on? Yes, cool. All right. So before I get started, I want to pose a mystery to you. Okay. Let's consider the following situation. Okay. Let's say we have a horizontal channel. Okay, we have flow in a horizontal channel that undergoes a smooth transition in the elevation of the bottom. Okay, so we have a flow in a horizontal channel. We have water coming in from upstream. And the channel bottom undergoes a smooth transition in depth. Let's just say that the height of this speed bump is given by delta zeta naught. That's what we're going to call it. Okay. So we have flow coming into this horizontal channel. And the question I want to pose to you is, what happens to this water surface elevation as it passes over this bump? What do you think happens to the water surface elevation as it passes over the bump? It increases. Okay, let's go through, let's just give 3 different options. Let's assume that no energy dissipation occurs. So no energy dissipation at this bump. It's a smooth bump. There's 3 options I want you to consider, okay? 1, the water goes up. Second, the water goes down. Or third, the water level stays the same. Okay, and let's just define a couple of variables. Let's call the depth at the upstream end h1, and let's say it's moving with a velocity u1. Okay, so let's do a quick poll here. Who thinks that the water surface elevation is going to go up? Just one? Just one? 1, 2? Okay. So we have 2 votes for the water surface elevation goes up. Who thinks that the water surface elevation goes down? 1. Just 1 vote? Okay. And who thinks the water surface elevation stays the same? Okay, that's pretty much everybody. So I will write a lot, okay? There's a lot of votes for water surface elevation, stays the same. Okay, so we're gonna come back to this later on. I'm not gonna reveal the answer just yet. Oh, there's a 4th option. Who thinks that I'm giving you a trick question? Okay, I would say maybe like 6, 8 people. 6, 8 people think I'm giving a trick question. Let's say 6 people. Okay, well, we'll come back to this. I won't reveal the answer just yet. But in order to answer this question, we're going to have to use the energy equation. Who remembers the energy equation from hydraulics? Ooh, that's not a lot. How many people remember the energy equation from hydraulics? Okay, what does the energy equation say? Just someone raise their hand and tell me. What does the energy equation say? Yes? Right, right. So yeah, so basically it's saying that energy is conserved over some distance along the channel. Okay, and I'm going to show you, it seems that the energy equation might, need some jogging in your memory. So I'm going to go through the energy equation, and I'm going to show you how we can derive it from first principles so that you don't just have to memorize it. And like most of the equations we use in this class, the energy equation can be derived from the Saint-Venant equations. Under the following assumptions. First, the flow is steady state. Okay, in other words, all of the time derivatives are equal to 0. Second, no lateral inflow. So no lateral inflow is coming into the channel. And 3, we integrate from an upstream point, which I'll call x1, to a downstream point, x2. Okay, so what I'm going to do next is I'm going to derive the energy equation, and then I'm going to give you an example to work on applying the energy equation to a small problem, okay? Okay, so let me just kind of give you a visual of what we're going to be doing here. Okay, so we have some channel here. It has some water flowing in it, and the water may not be uniform. It may vary in space, but it's going to be constant in time. Okay, the upstream end, we have some depth h1. The downstream end, we have some depth h2. At the upstream end, we have a spatial coordinate x1. The downstream end, we're at spatial coordinate x2. The upstream end, we have velocity u1. The downstream end, we have some velocity u2. It may not be the same. And we will call the elevation of the bottom above some datum. We will call, for the upstream end, we'll call it z1. And for the downstream end, we'll call it z2. Right? And this may be the elevation with respect to sea level, for instance. Okay. So these are the variables we'll be using. And we're going to integrate the St. Venant equations from x1 to x2, and from that, we will get the energy equation. Okay. So this is a really important equation. We're going to be using it a lot in this class. It's used a lot in solvers. It's used in Heckgrass for the static solver, for instance. So it is important to know. Okay. So as I promised, we can derive this from the St. Venant equations. So let's write down our St. Venant equations. We have, for continuity, dA by dt plus dq by dx is equal to the lateral inflow. And for momentum, we have dq by dt plus dqu by dx plus acceleration due to gravity times the cross-sectional area times quantity dh dx, that's the slope of the water surface, minus the bed slope plus the friction slope is equal to 0. So remember the assumptions I told you about. We are going to assume that the system is at steady state, which means this term goes to 0. This term goes to 0. And remember, I also told you that the lateral inflow into the channel is also 0. So this implies that, what does this imply about dq dx? It's also 0. Okay. With that in mind, we can simplify this term here. What does this term here become if dq dx is equal to 0? Yes, this becomes q du dx. Does anyone, okay, does everyone understand where this came from? So this is a property of calculus. If you remember the product rule, for instance, if we have dqu dx, this is equal to q du dx plus u dq dx. Right? If this term is equal to 0, this becomes q times du dx. So very good. Yes. No, for steady state, I just mean that the time varying components are constant. So uniform flow would cancel those out, yes. For steady state, it just means that the time derivatives are equal to 0. Okay. So we have dqu dx is equal to q times du dx. And therefore, we can factor out that q. So we get q du dx plus ga dh dx minus the bottom slope plus the friction slope is equal to 0. Now, what I'm going to do next is I'm going to take this expression and we can divide by GA. Okay, so what's going to happen to this first term when I divide by GA? What's Q divided by A? Q divided by A is U. Let's go ahead and write that down. We will end up with U over G times du dx plus dh dx, that is the slope of the water surface. And I'm just going to move S naught and SF over to the other side. So we'll end up with U over G times du dx plus dh dx is equal to the bottom slope minus the friction slope. Okay, so what is another way that we can express the bottom slope? Can we express the bottom slope as something divided by dx? Almost. Dx would be the length. So this is, right, the change in elevation. So this would be dz dx. And what about this term here? What is the friction slope again? It's the slope of what? The energy grade line. So I'm just going to call this dE by dz. Sorry, dE by dx. Sorry. So this is the slope of the energy grade line. Okay, so we can write this all in terms of derivatives with respect to dx. So we have U over G du dx plus dH dx is equal to dz dx minus dE dx. And with that, we can integrate this with respect to x from some point x1 to the downstream point x2 to arrive at the energy equation, okay? So I'm going to take this whole thing and I'm going to integrate it from x1 to x2. Okay, so let's just do that for each side. X1, x2, we can pull out the U over G. So we end up with U over G times du dx plus the integral from x1 to x2 of dh dx is equal to the integral from x1 to x2 dz dx minus the integral from x1 to x2 of dE dx. Okay, so we have each of these integrals here. And note that for each of them, we have a dx in the numerator as the integrand and also a dx in the denominator. Note that this isn't literally a numerator and denominator, but you can think of it like that. So essentially for each of these terms where you have dx in the denominator, dx in the numerator, these cancel out. Oh, sorry, actually I can't take this u out. So this is 1 over g, sorry about that. Okay. And what we'll end up with is 1 over g times the integral of u du plus the integral of dh is equal to the integral of dz minus the integral of dE. Okay, and we lost our x integrand, but we can just integrate these. We can change the limits of integration. So we integrate u from u1 to u2. This is equivalent. We can integrate dh from h1 to h2. We can integrate dz from z1 to z2. We can integrate dE from e1 to e2. Okay, so let's evaluate each of these integrals. What is the integral of this expression here? Let's just think about it in terms of the indefinite integral. 1/2 u squared, exactly. Okay, so I'll just write the indefinite integral down here. So this will be 1/2 u squared. This will evaluate to, if we just think about the indefinite integral, just h. And similarly, this will evaluate to z. This will evaluate to e. Okay, so we can go and get the definite integral by evaluating it for these limits. And what we'll end up with is u2 squared over 2g minus u1 squared over 2g plus h2 minus h1 is equal to z2 minus z1 plus e2 minus e1. And as an aside, I'm just going to define EL. This is the head loss. I'm going to define this as E1 minus E2. And with that, we can rearrange this to give the energy equation. Okay, so I'll write it out in the form that you're probably more familiar with. This is the energy equation. Okay, we will have u1 squared over 2g plus h1 plus z1 is equal to u2 squared over 2g plus h2 plus z2 plus the head loss. Okay, does this look familiar? Yes, cool. So this is the energy equation. It states that energy is conserved over this open channel section. And note, what are the units on this equation? Okay, so this is in units of length. So this is expressed in terms of the hydraulic head. Okay. Let me just make a note here. We have different names for each of these components. So the total head is equal to just the total head on each of the sides, h plus z plus u squared over 2g. The velocity head is equal to just this component due to the velocity, so that'll be u squared over 2g. And the piezometric head is essentially the component due to the potential energy, which is h plus z. Okay, so those are just some terms that you will want to know the remainder of the course. There's different components of these heads and they are called different things. Okay, are there any questions about that derivation before I move on? Okay, I'm going to give you a quick example to work on, just to kind of test your skills here. Okay, I'm going to tie in the energy equation back with something we talked about last time. Okay, so let's say we have uniform flow in an open channel. Okay, note that this is a rectangular open channel. Okay, and I'm going to say that the top width B or the bottom width B is equal to 8 feet. Okay, at an upstream point, the depth H1 is equal to 2 feet. The flow is equal to 38.5 cubic feet per second. Okay, and our Manning's roughness coefficient is equal to 0.015. Okay, so what is the total head loss due to friction uh, 10,000 feet downstream? So I will make a quick drawing for you. We have an open channel. So we have an open channel. It has uniform flow moving through it. Depth at the upper end is H1. Depth at the lower end is H2. The discharge at the upper end is Q1. Discharge at the lower end is Q2. This is 0.1 here. This is 0.2 here. This has the bottom elevation Z1, bottom elevation Z2, and this is 10,000 feet in length. I want you to find the total head loss due to friction over this length. Okay, so I'll give you about 2 to 5 minutes to work on that. Okay. All right. Let's. Does anyone want to volunteer and answer? Anyone want to volunteer and answer? Yeah. It's the answer. Okay, the answer should be 4 feet. The answer should be 4 feet. So let's go through how we can solve this problem really quick. Okay, so let's focus up here, please. All right, I'm going to show how to solve this problem. Okay, so we have uniform flow in a rectangular open channel. At the upstream end, we have depth H1, discharge Q1. At the downstream end, we have depth H2, discharge Q2. So let's write out the energy equation. We have, let's say we have H1 plus Z1 plus U1 squared over 2G is equal to H2 plus Z2 plus U2 squared over 2G plus our head loss. Okay. So if we have uniform flow, what does that imply about H1 versus H2? They're the same. All right. What does it imply about U1 versus U2? They're also the same. So we can reduce this problem to the head loss is equal to Z1 minus Z2. Okay, how can we compute Z1 minus Z2? Yes. Exactly. So we can solve the problem by using Manning's equation, which relates the depth, the discharge, and the slope. So Manning's equation is given by phi over n times a times the hydraulic radius to the 2/3 power times the square root of the bottom slope. Note that, let me just as an aside here, the slope is equal to z1 minus z2 over delta x. Therefore, z1 minus z2 is equal to the slope times delta x. Okay, so if we solve this, what you should get is that the slope is 0.0004 feet per feet. So this is the same situation we looked at in the last class, which was how I knew the slope. So you can compute the head loss simply by multiplying the slope times our distance, 10,000 feet. And that will give us a head loss of 4 feet. All right. So what does this tell us about another thing about uniform flow? What's a general rule we can say about uniform flow and the head loss? Exactly. The head loss for uniform flow is exactly equal to the change in elevation of the water surface. Okay. Great. Okay. So we have a new equation now. We have our energy equation. Maybe we can use this energy equation to go back and look at our original mystery problem. Okay, so we have a H1 and a U1. We have a change in the bottom elevation, and we also have, a H2 and a U2. But we actually don't have enough information yet to solve this problem. Okay. And what you'll find is that there are actual multiple depths that can occur at this point, depending on your flow conditions. Okay. So before we can solve our mystery problem, we first need to revisit another topic from hydraulics, and that is specific energy and critical flow. Okay. So let's talk about specific energy. Does anyone remember specific energy, what the definition is? So for our energy equation, we have that the total head is equal to the depth of the water plus the bottom elevation plus the velocity head. The specific energy is just the depth head plus the velocity head. Okay, so the specific energy for a given discharge Q the specific energy is defined as follows. E is equal to H plus U squared over 2G. And then in other words, it's the component of the energy due to the depth of the water, as well as the component of the energy due to the velocity of the water. Okay, and you can think of it the specific energy as the energy that can be flipped or traded between the depth component and the velocity component. So I'm just going to say the energy that can be traded between the depth head and velocity head. So let's go ahead and draw a diagram of the specific energy. As I mentioned, the specific energy is given for a particular discharge. So each discharge Q has its own specific energy curve. Let's go ahead and draw this out. We have our y-axis here. We have our x-axis here. On our y-axis, we're going to let this be the depth. And our x-axis is going to be the specific energy. Let me write it a little bit more to the left. E is equal to h plus u squared over 2g. Okay, so you can note that right away, we can draw a diagonal line with a slope of 1 from the origin. And what does this represent? This is specific energy is equal to the depth, okay? So this line will be if the specific energy is exactly equal to the depth. In other words, there's no energy component in velocity. All of the energy is in the depth component, okay? And for a given discharge Q, we can draw our specific energy curve based on this equation, h plus u squared over 2g. And our specific energy curve will look like this. It'll be this kind of quadratic looking curve that comes down like this, and then comes this way. Okay, so note that this is for a constant Q. This is for a constant discharge. So Q is the same along this curve. Every discharge has its own unique specific energy curve. Okay, and we could look at different points along this curve. Let's go ahead and show how they would map onto a channel section. So I'm going to draw a little channel section here. Okay, and for a given Q, we can have different depths associated with that discharge. Okay, so we might have a depth up here. We might have a depth over here. And we might have a depth even lower than that down here. We can map those depths onto our specific energy curve. So let's draw a line from our channel section to the specific energy curve. Okay, so these points where the lines are intersecting with the specific energy curve, these represent the specific energy for a given depth. Okay. So note that for this point up here, we have a given discharge Q, and we have this high depth associated with that discharge. And note that for this case, the majority of the specific energy is due to the depth component, and only this tiny sliver here is due to the u squared over 2g component. Okay, so for this point up here on the specific energy curve, most of the energy is in the depth component. Okay, for this point down here, we have that a small amount of energy is due to the depth, and a majority of the energy is due to the velocity component. And for this point in the middle, we have, roughly equal amounts of energy is due to the depth and to the velocity head. Okay, so you may remember from hydraulics that these different points on this curve represent different types of flow. Okay, so if you have flow where the majority of the energy is in the depth component or the potential energy component, do you remember what the name for that kind of flow is? Subcritical. And if the majority of the energy is in the velocity component, what is that called? Supercritical. So I'm going to draw a little dividing line here. Okay, and we'll say that the points on this side of the line are subcritical. And the points on this side of the line here are supercritical. this point here, what do we call this? Critical. This is, I'll just write it down here. This is critical flow. Okay, now how might we find this point on the curve given our equation for specific energy? This is the inflection point of our curve. It's at a local minimum, right? It's the minimum specific energy for a given discharge with respect to the depth. Okay, yes?
Is the H you have on the y-axis the same H that's included in the energy?
Yes. So this is E is a function of H. It's a function of H for our given discharge. Yes. Okay, so we can find this critical point by taking the derivative, right? Oh, is that what you were about to say? Yeah. So we can find our critical depth by taking the derivative of this curve. So let's say we have this plot here. Let's just go ahead and flip it so it's a bit more familiar looking. We'll put E on the y-axis and H on the x-axis. This is E equals H plus U squared over 2G. Okay, and we will have a curve that looks like this. And if we want to find the critical depth, it's the point where the specific energy is minimum for a given discharge Q. Okay, so we can find this point by taking the derivative of E with respect to H and setting it equal to 0, right? This is how we find the minimum of a function, okay? Find the minimum of a continuous function. So let's go ahead and do that. We're going to take the derivative of our specific energy with respect to the depth, and we're going to set it equal to 0. So let's write that out. We have d by dh. What's our expression for E again? What's our expression for the specific energy? Exactly, H plus U squared over 2G. Okay, so let's take the derivative of each of these components. What is d by dh of H? 1. Okay, so that was easy. Okay, now we got to take d by dh of U squared over 2G. Are there any ideas how we can do this? Yes. Yes. Exactly. So we're going to take this U. We know that the discharge is equal to U times the cross-sectional area, and thus U is equal to the discharge divided by the cross-sectional area. So we're going to substitute that in here. We have d by dh of Q squared over 2G times A squared. Okay. Now remember, for a given specific energy, Q is what? Constant. So we can take it out of this derivative. We have Q squared over 2G times d by dh of 1 over A squared, right? Okay. So now we just need to take the derivative of the cross-sectional area with respect to the depth. And we know that the cross-sectional area is a function of the depth, right? So this should be doable, okay? So let's rewrite this. This is Q squared over 2G times d by dh of A to the negative 2 power. Okay. How might we do this? One way we might do this is by the chain rule, right? So in calculus, who remembers the chain rule? Cool. This is an important one. If you have a function f and you're taking the derivative of f with respect to some variable x, you can rewrite this as the derivative of f with respect to another function g times dg by dx, right? So we're going to apply the chain rule here. We're going to have q squared over 2g times d of a to the negative 2 by dA times dA by dH. Okay, now this we should be able to evaluate, right? What does this evaluate to? So what would the derivative of x to the negative 2 power with respect to x be? Yeah, so this will be negative 2 times the cross-sectional area to the negative 3 power. Okay, so it's just the same as taking the power rule for x, right? You'll have this term times this other derivative, the derivative of the cross-sectional area with respect to the depth. Now, there's a special identity for this term here, and I'm not sure if they covered it in hydraulics or not. What is the change in the area of flow with respect to the depth? Let's just look at a channel section. And let's say we have some depth in the channel. This is really important, by the way. We have a depth in the channel H. We have an area of flow A. And we have a change in depth of dH. What is the incremental change in the area with respect to our incremental change in the depth? The what width? The differential. Almost the width of what part of the channel? Top width, exactly. So let's just call that T. Okay, this is really important. This appears a lot in open channel flow. The derivative of the cross-sectional area with respect to the depth is equal to T, which is the top width. Great. Was that covered in hydraulics? Yeah, okay. Okay, so we're almost done. We can substitute T for dA by dH. And so our expression ends up being the following: 0 is equal to dE by dH. Okay, and this is equal to d by dH of h plus u squared over 2g. Substituting in the values that we just wrote, this will end up being 1 minus q squared times the top width over the acceleration due to gravity times the cross-sectional area cubed. Let's go ahead and rearrange this. And we get the following. We get that 1 is equal to q squared times the top width over g times a cubed. And let's simplify it a bit. We have this q squared over this a cubed. How can we express this in terms of the velocity now? Yeah, so this becomes u squared times t divided by GA is equal to 1. Okay, and this is the equation that characterizes critical flow. This works for any channel cross section. If the flow is critical, this equation has to hold true. Okay. So when you're solving problems involving critical flow, you can always use this equation to relate the depth and discharge. Okay. Great. So this is the equation that characterizes critical flow. In hydraulics, how did you usually identify whether a flow was critical or subcritical or supercritical? What did you use? The Froude number, okay? So we can derive the Froude number from this expression as well. Essentially, all we need to do is take the square root of both sides. Okay. Okay, so if we take the square root of both sides, we get u times square root of t over square root of GA. And this is equal to the Froude number. Okay. So we can use this to characterize whether the flow is critical, supercritical, or subcritical. If this expression is less than 1, it is subcritical. If it is equal to 1, well, then from this equation here, we have that the flow has to be critical. And if it's greater than 1, the flow is supercritical. Because that's just how the Froude number is defined. Note that for the case of critical flow, the other side will just be 1 still. Square root of 1 is 1. So the Froude number is just defined by taking the square root of this term, basically. Yeah. Right. So the Froude number essentially describes the ratio of the inertial forces, the forces due to velocity, to the gravitational forces. Okay. That is what the Froude number represents. And with that, we actually have enough to go back and solve our mystery problem. Okay. Are there any questions before I move on? Any questions? All right, let's go back and let's try to solve our mystery problem. And I'm going to give you some numbers now. Oh, was there a question about the?
Little bit.
Yeah.
So could you just start with C, because in hydraulics, we're learning the top was, I think it was in that viscosity. It was.
If it's viscosity, it's probably the Reynolds number. Oh,
No, but I was just. Taylor's. Hydraulics.
okay. Send that to me after class and I'll try to figure it out. But we know that this has to be true because we just derived it from first principles, right? Yeah. Okay, cool. Okay, cool. So let's go back to our mystery problem. Let's put some numbers on it this time. I'll just draw out the problem again. So we have our channel, it's horizontal. We have a bump with an elevation of delta zeta naught. We have flow coming in at the upstream end. Okay, and this flow has a depth of h1 and a velocity of u1. Okay, and let's put some numbers on this. So let's say that h1 is equal to 3 meters. U1 is equal to 3. Let me just check and make sure I have my numbers right. 3 meters per second. Let's say that the bottom width of the channel is 3 meters. And this is a rectangular channel. And let's say that delta zeta naught is equal to 0.3 meters. What we want to do is we want to find H2. And in doing so, we also want to find U2 as well. Okay, so let's go through this problem and try to solve it. We're going to solve this using the energy equation. I think I have just enough time to solve this problem today. Okay. So first, it's going to be helpful if we know the discharge in this channel. So let's go ahead and solve for that first. Let's solve for Q1. Q1, the discharge. So what would the discharge be in this case? How can we compute it from the variables that we know? I could, yeah, velocity times the bottom width times the depth. Okay. Okay, and what this will give us is, I believe this is 3 meters per second times 3 meters times 3 meters will give us 27 cubic meters per second. Okay. So the velocity at the upstream end is Q1. It's 27 cubic meters per second. Can we know what the velocity is at this point here? Oh, sorry. Can we know what the discharge is at this point here?
Yeah.
Yes. How do we know what the discharge is here? Right. If it's steady state, Q2 has to equal Q1. Otherwise, water would accumulate somewhere in the system, right? So we'll just call this Q. This is 27 cubic meters per second. Okay, so what we did essentially here was we applied continuity. Okay, so we know that the discharge at the upstream point has to equal the discharge at the bump. Okay, so with that, we can set up the energy equation. We have, let's just write it out as we usually do. We have H1 plus U1 squared over 2G is equal to H2 plus delta zeta naught plus U2 squared over 2G. Okay. So U1 is known, H1 is known. U2, we can write in terms of the discharge, and we're trying to solve for H2. Oh, and note that delta zeta naught is also known. Okay, so what we're trying to solve for essentially is this H2 here. Yes?
In this, we're assuming that there's no like head loss.
Oh, right. So let me just write that explicitly. This is a smooth transition with no energy losses. If you did have energy losses, this would be a different problem. Okay. Okay, so we can rewrite this now. We essentially want to get rid of this U2 and express it in terms of what we do know. So we can rewrite this as H1 plus U1 squared over 2G is equal to H2 plus delta zeta naught plus, how can we express U squared? Well, you already said it before. This is Q squared over 2G. And what's the cross-sectional area at this point? Yeah, H2 times B squared. So we can actually just write H2 squared, B squared. All right. Okay, and let's go ahead and just start substituting in known values. Let's clean things up a little bit. Okay, so if we substitute in our value for H1, we get 3 meters. The velocity component is 3 squared over 2 times 9.81 is equal to H2 plus our delta zeta naught term is 0.3 meters. And the velocity head term is equal to Q squared, which is 27 squared over 2 times 9.81 times, we know B squared is 3 squared times H2 squared. Okay, and let's just go ahead and get rid of some of these numbers. If we evaluate this, what we end up with is 3.1587 is equal to H2 plus 4.1284 divided by H2 squared. Okay. Now, what can we do here to solve this? Let's go ahead and multiply through by H2 squared. If we multiply through by H2 squared, what we will end up with is H2 cubed from this term plus minus 3.1587 times H2 squared plus 4.1284 is equal to 0. Great. And now you can see here that we have a cubic equation for our depth H2. How can we solve this? Find the roots. Okay, so I'm going to go ahead and do this in Python again. I have about 5 minutes. I think that's just about enough time to do this. Let's go ahead and do this again. So I'm doing this in Python. You can do this on your graphing calculator. Okay, just like last time. Sorry, can I have your attention? Are there any questions about, were there any questions about what I'm doing? Okay, so this operation you can perform on your graphing calculator. I'm just going to show you how to do it using a programming language. We're essentially just going to find the roots of this cubic polynomial, okay? Okay, so first I'm going to import my numerical library NumPy. And then to find the roots, we can just use this function np.roots. Okay, it returns the roots of a polynomial with coefficients given in P. Okay, so you give this function your coefficients of your polynomial, it will return the roots for you. Okay, so let's go ahead and do that. We'll say that our roots are equal to np.roots. And what are the coefficients of our polynomial again? So what's the coefficient of our highest order term? 1. Okay, 1. And our second highest order term is 3.187. What's our next term? 0. Exactly. Oh, sorry, you're right. This should be negative. And the final term is 1, 2, 8, 4. Okay. So we've evaluated that function. Let's see the result. Okay, our roots are 2.496, 1.65, and negative 0.996. All right. So we haven't solved our mystery yet. We still have 2 different answers to choose from, essentially. Okay. So we know that H2 is one of the following. It's either 2.496, 1.659, or negative 0.997. Okay. So right away, we can rule this one out. Okay, this one is non-physical. But now we have to choose between 2.496 or 1.659. Does anyone have any idea how we might go about choosing which one it is? What do you think these two numbers correspond to? Exactly. So which one is the subcritical and which one's the supercritical? My hearing is not very good. Could someone raise their hand and give me an answer? Yes. Yes, so this is the subcritical. And this is the supercritical. Okay, so we know it has to be one of these two. Does anyone have a guess for what it is, just based on intuition? Sorry? Supercritical, we got to vote for supercritical. Anyone think subcritical? Think subcritical? Another one for subcritical? Yeah. So it is the subcritical one, okay? And the answer is not obvious at first as to why, but we can see it by looking at our specific energy diagram, okay? So let's go ahead. I'll just write out the answer. H2 is equal to 2.496 meters, which means that the water surface elevation is equal to H2 plus delta zeta naught, which is equal to 2.796 meters. So the water surface went down. Awesome. All right, everyone who said it goes down, give yourself a pat on the back. Actually, it was a trick question because it depends on what your flow regime at the upstream end is. Okay. Yes. I'm sorry. My hearing is not very good. Can you ask that? I will show you why, but I think it's going to have to wait until next lecture. So the mystery continues. Okay.